Okay,
Yes,
okay,
already.
okay. So in this three paper, first two paper he has given the basic uh, results about the semi-total line graph and semi-total point graph. And in the third paper, he has told about the connectivity, then covering number, impedance number, planarity, uh, such type of properties he has elaborated in the paper 3. He got this idea from the coloring, because coloring of a graph is just assigning the colors to the vertices of a graph such that no two adjacent points are the same color, correct? And then the total coloring means assigning the colors to the points as well as the lines. Okay, assigning colors, points as well as lines, so that the no two adjacent or incident elements. Elements means here points and lines have the different color like that. So from that he got the idea about the semi-total coloring, semi-total line coloring, semi-total point coloring. From that first he got the idea, and then he defined the semi-total line graph and semi-total point graph. So I have shown here the screenshot of the paper. That is the first paper, semi-total graph of a graph. Okay, now he has done this work with his student S.B. Chikorimat in the year 1973. Okay, so this is the first cover page. This is the first page of the paper. Okay, just 2-3 pages I have scanned and I am showing here. So see here, he has mentioned here a semi-total line coloring of a graph G is a coloring of both the points and lines of G such that no two adjacent lines of G have the same color, and no point and a line incident with it have the same color. Thus, in this coloring, two adjacent points may have the same color. See here. In this definition, the two adjacent points may have the same color, but the adjacent line should have the different color, and the line and the point incident to it should have the different colors. So for such coloring he called semi-total line coloring. Similarly, semi-total point coloring, that is coloring of both points and lines such that no two adjacent points of G have the same color, and the point and line incident with it do not have the same color. Okay, so first he defined the coloring, semi-total line coloring and semi-total point coloring. Then we'll go for this. So this is the second page of that paper. Okay, now we'll start with the basic definition. So here we are considering the graph G with the vertex set V of G, and the vertices are labeled as V1, V2, Vn, and the edge set is Eg with edges are E1, E2, En. And as many of you know, that degree of a vertex is nothing but the number of edges incident to that point, usually denoted of Di or D of Vi. Okay, and if the degree of each vertex is equal to R, then we call graph is regular. Okay, regular graph with the degree R. Now come to the semi-total line graph definition. Okay, so instead of talking in terms of coloring, we'll do directly here now. The semi-total line graph of a graph G, usually denoted by T1G, is a graph with vertex set will be union of the vertices and the edges. Okay, and two vertices in this semi-total line graph are adjacent if one is a vertex and other is an edge incident to it in G, or both are edges adjacent in G. Okay, so here edges, if two edges are adjacent in G, then we can put a line in the semi-total line graph also. And if the line and point incident to each other, we'll put the line here. Okay, same way semi-total point graph. Okay, here spelling mistake, point graph it is. Semi-total point graph, we'll denote this by T2G. It is a graph with vertex set, again same union of vertex set of G and the edge set of G, and two vertices in T2 are adjacent if they are adjacent vertices in G, or one is a vertex and other is an edge incident to it in G. Okay, now from this figure you will come to know this is a graph. Okay, the first figure, a graph G with labeled as vertices V1, V2, V3, V4, and the edges are E1, E2, E3, E4. So semi-total line graph, that is T1G. So here vertices will be the both vertices as well as the edges of G, correct? And in this the if correspond here edges are adjacent, okay, in G, then you have to make here adjacent. Here for example E1 and E2 are adjacent, so we have put here line E1 to E2. Similarly E2, E4 are adjacent, so we have put the line E2, E4. And the vertex and edge is incident. For example, here E1 is incident to V1 and V2. Okay, so E1 should be adjacent here to V1 and V2. Similarly, here E4 is incident with V3 and V4. So E4 is incident with means adjacent here with V3, V4. So this is a semi-total line graph. Same way, semi-total point graph. So again, in the semi-total point graph, the vertex set will be the union of the vertices and the edges of G. Okay, and if the vertices are adjacent, we'll put here line. For example, see here V1, V2 adjacent, so we'll put here line V1, V2. Similarly, here V3, V4 adjacent, so we'll put here line V3, V4. And corresponding to E1, now E2 is incident with V3 and V2. E2 is incident with V3 and V2. So E2 is here adjacent with V2 and V3. Similarly, E4 with incident with V3, V4. So it is V3, V4. Okay. So this is a semi-total line graph. This is a semi-total point graph. And total graph is another one that is usually denoted by T of G. So there you have to take the vertex, it will be union of the vertices and the edges, and the two elements. Elements means here either point or edges. So two elements of total graph are adjacent if and only if they are corresponding adjacent elements or incident elements in G. Okay, but here in this talk we are talking only with the semi-total line graph and semi-total point graph. So algorithm what given by Sampath Kumar in his paper. It is simple way one can draw this semi-total line graph and semi-total point graph. What you have to make? The first algorithm, just here. On each line of G, take a new point and join a pair of such new points if and only if they are on the adjacent lines of G. So resulting graph will be T1G. See here. So this is a graph G. On each line, you take a new point here, E1, E2, E3, E4. So we have taken here one. And join those points if and only the corresponding lines are adjacent here. So here E1 and E2 are adjacent, so we have to join there. E1 and E3 is adjacent, so we have to join here. So with that algorithm, one can get the semi-total line graph. Same way, semi-total point graph. So corresponding to each line of G, take a new vertex W and join it on the vertices U and V. Means you have to put a triangle on each line in the G. So resulting graph will be T2G. See here. So take a graph G first here. This is a graph G, and on each line put a triangle. So here we are taken corresponding to each line we are taken up say vertex W. So here W means E1 and make it adjacent to its incident vertices. Okay. So on this line you have to make triangle. On this line you have to make triangle. So we'll get the resulting graph as a semi-total point graph. So this is a simple way one can draw the semi-total line graph and semi-total point graph. Okay, so the degrees of the points in this semi-total graphs. If U is a point of a vertex of a graph, original graph, then the degree of a point in the semi-total line graph will be simply the degree of U, and in the semi-total point graph it is twice the degree of U. Okay, see here. For example, say V2. So V2, the degree of V2 will be same as degree of V2 in the G. See here, 3, 3. Whereas in the T2, it is twice. So here it is 3. So it becomes 2 times, means 6. So you get the 6. And if the point is a line, corresponding line with the endpoints UV, then the degree of that point E in the semi-total line graph will be degree of U plus degree of V. And in the semi-total point graph, it is simply 2. Okay. See here. For example, you to consider this E2. Okay. So degree of E2 will be degree of V2 plus V3, that is 3 plus 2, 5. So see here, degree of E2 is 5. Okay. And in the T2, the degree of E2 is always 2. Here 2, 2, 2. For each edge, it is 2 only. So by observation, easily one can tell this. Okay. So degrees of the points in the semi-total point graph as well as the line graph. Next. So delta G is the maximum degree of a graph G, and delta 1G denotes the maximum of the degrees of edges minus 2 among all the edges. So degree of edge means if suppose E is having the endpoints U and V, then the degree of the edge is degree of U plus degree of V minus 2. So this quantity will be simply degree of U plus degree of V, where U and V are adjacent, means the endpoints of edge. So delta 1 is denoted by that. So for any graph G, the maximum degree of the semi-total line graph is delta 1G. That is maximum of the degree of E minus 2. And the maximum degree of semi-total point graph is twice the maximum degree of G. Next, the chromatic number. So chromatic number is the minimum number of colors required to color the graph. Okay. So for any graph G, the delta means the chromatic number of T1G lies between delta G plus 1 and delta 1G plus 1. Whereas chromatic number of T2, that is semi-total point graph, is 3 if the chromatic number of original graph is 2, and if it is not 2, it will be simply chromatic number of G. See the proof, just outline here. Now T1G contains Kp as a subgraph where P is a delta G plus 1. Okay. The semi-total line graph contains a complete graph of order delta G plus 1, and hence the chromatic number of T1G will be more than or equal to delta G plus 1. Okay. So the left hand side is established. Now for the right hand side inequality, we know that for any graph, the chromatic number is always less than its maximum degree plus 1. Correct. So chromatic number of T1G is less than maximum degree of T1G plus 1, and maximum degree of T1G is nothing but delta 1G. Okay. Here from this result, maximum degree of semi-total line graph is delta 1G. So you got this second inequality. And for the second result, by the construction, from the construction of the T2G, easily one can observe it is 3 if the chromatic number of G is 2, and if it is not 2, the chromatic number of the semi-total point graph is same as the chromatic number of the graph G, that is underlying graph G. Now characterization of the semi-total graph. Here NU, this notation, this is a closed neighborhood. Okay, neighborhood of a point is a set of the all its neighbors. Okay, and including that point, it is a closed neighborhood. Okay, so NU denotes here closed neighborhood of a vertex U. So characterization, a connected graph G is a semi-total line graph of some graph H. Okay, if and only the vertex set of G can be partitioned into two sets S1, S2, such that for every W in S1, there exists a unique pair of distinct vertices UV in S2 satisfying following conditions. Okay, one can partition the vertex set of G as S1, S2. So for every vertex of S1, there must exist distinct vertices U and V in the other set S2 with following conditions. That is, U and V are adjacent to W, and degree of W will be degree of U plus degree of V. And the subgraph of G induced by the closed neighborhood of U union closed neighborhood of V is Kp plus 1 dot Kq plus 1. What is meant by this dot? It is identifying one point of this complete graph with the one point of this complete graph. Identifying one point from the Kp1 with the one point of Kq1. Okay. So Kp plus 1 has P plus 1, Kq plus 1 has Q plus 1 points. And when you identify this one point, the total number of points in this graph will be P plus Q plus 1. So if the subgraph of G induced by this union is this one, where P is a degree of U and degree of Q is a degree of P. Okay, then we can say that G is a semi-total line graph of some graph H. Okay. Now block graph. First of all, what is meant by block graph? Block is a non-separable induced subgraph of G. That is, it has no cut point as well as bridge. Okay, maximal subgraph without cut point and bridge. So block graph BG of a graph G is a graph whose vertex has the one-to-one correspondence with the blocks of G. So blocks becomes the points of the G becomes the points of B of G, and two vertices are adjacent in BG if and only the corresponding blocks share a common point. Just like our definition of line graph. In the line graph, we take the vertices as the corresponding the lines of G, and the 2 points in the line G are adjacent if and only the corresponding lines share a common point. So same way here, instead of line, here it is a blocks. Okay. So from this, for a graph G, the block graph of semi-total line graph is always tree. Okay, the block graph of the semi-total line graph is always tree. And if G plus is a graph obtained from G by attaching one pendant vertex, that is a corona graph. Okay, corona graph means with corona means attaching only one point to each vertex of G. Okay, then the line graph of this G plus is always the semi-total line graph. Okay, the line graph of G plus is a semi-total line graph of G. Next, planarity. Okay, regarding the planarity, the semi-total line graph is planar if and only if G is planar and the maximum degree is less than or equal to 3. Then T1G is outer planar if and only if the maximum degree is less than or equal to 2. Planar means the graph can be drawn on a plane such that no two lines intersect with each other. Okay, and the outer planar means all the points. Okay, all the points lie in the same face, that is outer face. That graph is called the outer planar graph. Okay, so if the semi-total point graph, line graph is planar if and only G is a planar and maximum degree is less than or equal to 3. Is outer planar if and only if the maximum degree is less than or equal to 2. So maximum degree is less than or equal to 2 means either it is a matching or path or cycles. Okay, next, the T2G, that is a semi-total point graph. It is a planar if and only if G is a planar, and it is outer planar if and only if G is a outer planar. Okay, here only if G is planar or outer planar, then the corresponding means semi-total point graph of that graph is also planar or outer planar. Whereas in the semi-total line graph, additional condition is there with maximum degree. Okay. Now see the traversability. Okay, all these results done by the Professor E. Sampath Kumar and his student Chikkodi Mutt in those 3 papers. Okay. So traversability, that is T1G is Eulerian if and only if G is Eulerian. So Eulerian means a graph where the Eulerian tail exists, or in other words, the degree of each point of G is even number. Okay, degree of each point is even, then the graph is Eulerian. So here semi-total point, semi-total line graph is Eulerian if and only if G is Eulerian, and semi-total point graph is always Eulerian. Is always, because the degree of each point is here even. See here, see in the semi-total point graph, that is T2G, the degree of each point here 2 times degree of m, so even number. And if it is age, then it is 2. Okay, so degree of each point in the semi-total point graph is even. So naturally the graph is, that is the semi-total point graph is a Eulerian graph. Okay. Next, if G is a Hamiltonian, then T1G is a Hamiltonian. If G is Hamiltonian, then T1N is Hamiltonian. T1N means the iterative semi-total line graph. Means T1, for example, T12 means a semi-total line graph of T1. Okay, then again you have to take a semi-total graph, again you have to take semi-total graph, like that. Okay, so if G is Hamiltonian, then T1N G is Hamiltonian. It is directly from this previous result, this first result. Okay, see here, G is Hamiltonian, then T1G is Hamiltonian. Now T1G is Hamiltonian, so it's a semi-total line graph, that is T1 square G, means second what to say, semi-total line graph of G is Hamiltonian. That is Hamiltonian. Then again take its semi-total line graph, again Hamiltonian. Okay, so for any n more than or equal to 1, it is Hamiltonian. Next, if T1G is Hamiltonian, then line graph LG is Hamiltonian. See here, T1G is Hamiltonian, then line graph of G is Hamiltonian, and T2G is Hamiltonian if and only if G is either K2 or cycle. Okay. Now the some results on the covering number and independence number of the semi-total graphs. So point covering number means minimum number of points which covers all the lines. Covering up a line with the points means that point is incident with the line. Okay. So point covering number is the minimum number of points which covers all the lines. Line covering means a minimum number of lines which covers all the points. Okay. Independence number, point independence number is a maximum number of independent points. Independent points means no two a set is subset of a vertex set is said to be independent if the no two points are adjacent. Okay, so maximum number of independent points is called the point independence number, and similarly the maximum number of independent lines is called the line independence number. Okay, these are the notation: alpha naught, alpha 1, beta and beta. Okay, so for this graph, alpha naught is 2. So minimum 2 points are needed here to cover all the lines. For example, this point, this middle V2, V2 covers this line, and V2 V4. Now one line left. So to cover that, we require one more point. So either you can take V3 or V4. So 2 points are needed here. So point covering number of this graph is 2. Similarly, the line covering number. So minimum number of lines required to cover all the points. If you consider this line V1, V2, which covers the points V1 and V2, and another line is V3, V4 here to cover the points V3. So these two lines are required to cover all the points. So alpha 1 of this graph is 2. Similarly, the maximum number of independent points. So we can take V1 and V3 or V1 and V4. Okay, V1 and V4. We can't add one more point. So this is the maximum set. So beta naught is 2. Similarly, the beta 1, that is maximum number of independent lines. That is this line V1, V2, and another line is V3, independent. So for this particular graph, all the values are 2 only here. That is alpha naught, alpha 1, beta, and beta. Okay. And here, this is a known result given by Galli. For any graph G with n points, alpha naught plus beta 1 is say equal to n is equal to alpha 1 plus beta 1. Correct? For any graph G with n points, the alpha naught, that is point covering number, plus point independence number is equal to n, and which is equal to the line covering number plus line independent number. Okay. So this result used by Sampath Kumar and student to establish the covering number and independence number of the semi-total graphs. Okay. So they observe that for a graph G with n points and m lines, the point covering number of T1G is m, the line covering number of T1G is n plus m by 2 with ceiling function. Then point independence number is n, and the line independence number is n plus m by 2 with floor. And for the T2, that is the semi-total point graph, the alpha naught and alpha 1 is n, and beta naught and beta 1 is m. Okay. So this Galli's result is satisfied for this semi-total graphs also, because this is a result for any graph, any graph. So naturally it should satisfy here also. Okay. So so far I told the results on semi-total graph, both line graph and point graph, which is done by Professor E. Sampath Kumar in his seminal paper, the 3 papers, which is published in the 1973. Now I am covering the other results done by us with a different concept on the semi-total graphs only. Okay, semi-total graphs. So first, adjacency polynomial. So adjacency matrix is a graph with it is a adjacency matrix is a matrix, square matrix of order n, where ijth entry is 1 if the vertices vi and vj are adjacent, otherwise 0. Okay, and the characteristic polynomial of this matrix is called the characteristic polynomial of a graph, denoted by phi g lambda. I is the identity matrix, and the roots of these equations labeled as lambda 1, lambda 2, lambda n, they are called the eigenvalues, or sometimes a eigenvalues of G, and their collection is called the spectrum. And the sum of the absolute values of the eigenvalues is called the energy of a graph. So this is ordinary energy, or sometimes we call adjacency energy of a graph G. Summation of mod of lambda I is 1 to n. Okay. Another matrix, that is incidence matrix, denoted by B. Okay, indexed by the vertex set and the edge set. Okay, and the ijth entry of this B is 1 if the vertex Vi is incident to the edge Ej, otherwise 0. So one can observe that B into B transpose is always A plus D. A is an adjacency matrix and D is a diagonal matrix, whose diagonal entries are the degrees of the vertices. Okay, and if the regular, okay, it is a regular, then B transpose is A plus Ri. Okay, because this diagonal matrix D will be R into the identity matrix. So these results we are going to use for the further results. Okay, so this is given by the Katkovic, the characteristic polynomial of the semi-total line graph. So G is a graph with n points and m lines. Then the characteristic polynomial of the semi-total line graph can be expressed in this form: lambda raised to n minus 1 into lambda plus 1 raised to n into characteristic polynomial of the line graph with parameter lambda square minus 2 by lambda plus 1. Okay, I will outline the proof. See here. the vertices of T1G can be labeled in such a way that you can get the adjacency matrix of semi-total line graph as adjacency matrix of line graph. B transpose B is the incidence matrix of G minus B and O. O is a zero matrix. Okay, so one can label the vertices so that you can get the matrix adjacency matrix of T1G is this. Then applying the definition of the characteristic polynomial. So characteristic polynomial of T1G is nothing but the determinant of lambda I minus adjacency matrix of T1G. So putting here, you will get lambda IM minus ALG minus B transpose minus B and lambda IN. This is not minus B, it is a B. Okay, it's a B only. Then applying the known result from the linear algebra. For example, in the block determinant of the block matrix. So for example, set is M, N, P, Q. M and PQ, where M is a non-singular matrix, then the determinant will be determinant of M into determinant of Q minus P M inverse N. Okay, so using that result, we can express this in the form of this. We get lambda raised to N into this, and then simplifying, finally we will get the characteristic polynomial of the semi-total line graph in terms of the characteristic polynomial of the line graph of G with this parameter, lambda square minus 2 upon lambda plus 1. So if we know the characteristic polynomial of the line graph of G, one can get the characteristic polynomial of the T1G, that is semi-total line graph. Okay, and further there is a relation between the characteristic polynomial of the line graph and the characteristic polynomial of G if G is a regular. Okay, if G is a regular, easily one can get the eigenvalues if you know the eigenvalues of G. So if you know the eigenvalues of G for a regular graph, you can get the eigenvalues of LG, and once you know the eigenvalues of LG, you can get using this expression the eigenvalues of the T1G. Okay, see here, this is for the regular in particular. Okay. Next, for the semi-total point graph. So same way, if G is a regular graph on n points and m edges, then the characteristic polynomial of the semi-total point graph is given in this form. That is lambda raised to m minus n, lambda plus 1 raised to n, phi of G with this parameter, lambda square minus r by lambda plus 1. So here also one can label the vertices of T2 in such a that you will get the adjacency matrix of T2G in this form. Okay, and then using the definition of the characteristic polynomial, one can express the characteristic polynomial T2G in the form of this. Okay, that is lambda raised to m minus 1, lambda plus 1 raised to n, phi of G. So here, if we know the eigenvalues of a, but this result is for the regular graph, not for any graph. Whereas in the previous, this one we have shown for the any graph. Okay, this is for the regular graph. So if we know the eigenvalues of the graph G, adjacent eigenvalues, then using those and using this expression, one can get the eigenvalues of the semi-total point graph. Okay, next, degree subtraction adjacency polynomial. Okay, so first we will define the degree subtraction adjacency matrix. Okay, it is square matrix Dij, where Dij is that is ijth entry is the degree of Vi minus degree of Vj if Vi and Vj are adjacent, otherwise 0. Degree of Vi minus degree of Vj if Vi is adjacent to Vj, otherwise 0. And the characteristic one of this matrix is called the degree subtraction adjacency polynomial, and its eigenvalues or roots of this polynomial are denoted by xi1, xi2, xi n. And as defining for the ordinary graph energy, here also same way, the sum of the absolute values of these eigenvalues is called the degree subtraction adjacency energy. Now, since here degree of Vi minus degree of Vj, it is a square symmetric matrix. Okay, it is a square symmetric matrix. So its eigenvalues are either 0 or purely imaginary because of it is a square symmetric matrix. Okay, so as I told, the degree subtraction adjacency energy is defined in this form, similar to the ordinary energy, sum of the absolute values of the eigenvalues. Okay, then this is how we obtain for the semi-total line graph. If G is a regular graph with regularity more than 1 with n points and images, then the characteristic polynomial, that is degree subtraction adjacency polynomial of semi-total point graph, semi-total line graph is given by this minus 1 raised to n r to the power 2n xi raised to n minus phi of g, that is characteristic polynomial of g with this parameter. Okay, minus I square minus r cube by r square. So same technique is used, that is labeling the vertices in such a way that we will get this matrix, and then using that MNPQ formula where m is a non-singular. Okay, determinant of m into determinant of q minus pm minus n. Using that same technique as done previously. Okay, same technique can be used here also, and using that we will get the degree subtraction adjacent polynomial of semi-total line graph in this form. Okay, now see. Now see here, if suppose lambda 1, lambda 2, lambda n are the adjacency eigenvalue of G, and of course I is the square root of minus 1, then the DSA eigenvalue of T1G are 0, which are m minus n times, and the remaining are plus or minus IR into square root of r plus lambda. So if you know the adjacency eigenvalues of G, you can get the DSA eigenvalue of the semi-total line graph. Okay. Then similarly, for the semi-total point graph, the characteristic polynomial of the DSA matrix is xi raised to m plus n if r is 1. Okay, that is for the matching. Okay, and if r is more than or equal to 2, then you will get the characteristic polynomial in this form. Okay, so this term along with the characteristic polynomial means adjacency polynomial. This is of G with this parameter. Okay, I will skip the proof. Okay, because same technique we have used. Same technique again, labeling the vertices in such a way that you will get this form, and then applying that determinant of the block matrix, one can express the characteristic polynomial of the DSA matrix of T2G in this form. Okay, and then if you know the eigenvalues of the graph, then you can get the DSA eigenvalue of T2G. Okay, if this r is 1, then all the DSA eigenvalue of T2G are 0, and if r is more than 2, then the DSA of T2G are 0, m minus n times, and the remaining are in this form, plus or minus I square root 2r minus 2 into square root r plus lambda. Here this bold I is nothing but square root of minus 1. Okay. So from this result, we can observe that, okay, two different graphs having same eigenvalue are called the cospectral. So if G1 and G2 are adjacency cospectral with same regularity, then by above results, the graphs T1G1 and T1G2 or T2G1 and T2G2 form a pair of DSA cospectral, provided G1 and G2 are cospectral, adjacent cospectral. If they are adjacent cospectral, then the semi-total line graph as well as semi-total point graph also cospectral with respect to the DSA matrix. Okay, with respect to DSA matrix. Okay. Then from the knowing the eigenvalues, one can get the DSA energy. So DSA energy of the T1G is 0 if r is 1, because eigenvalues are 0 here. Otherwise, it is 2 into 2r minus 2 sum of square root of r plus lambda I. Okay. So depending on the value of lambda I, one can express this expression in the simpler form. And for the T2G, it is 2r summation of square root of r plus lambda I or any r. Okay. And from that, we can observe here the relation between the DSA energy of the subdivision graph in semi-total point graph, semi-total line graph. And that you can observe here, the DSA energy of subdivision graph is always less than the DSA energy of the semi-total point graph, and which is less than DSA energy of the semi-total line graph. Strictly less than it. Okay. Now come to the Sommer polynomial. First, what is meant by Sommer index? There are so many indices defined and people are working. So recently the Sommer index is introduced by the Ivan Gutman, okay, as summation of square root of the du square plus dv square. Du is a degree, okay, so square root of du square plus dv square for every adjacent pair. Sum is taken over every adjacent pair. So this is called the Sommer index. Then using Sommer index, they are defined the Sommer matrix. So in the Sommer matrix is also square matrix of order n, whose ijth entry will be square root of dvi square plus dvj square if vi and vj are adjacent, otherwise 0. So if there is an adjacency, then we will put the square root of square of the degree plus the square of the degree of other adjacent point, otherwise 0. And then as usual, the characteristic polynomial of this matrix is called the Sommer polynomial of G. So recently we obtained the result for the Sommer polynomial of the semi-total line graph as well as the point graph. So if, the most of the results in this talk are on the regular graph, okay, not for any graph. For any graph, it is not that easy to get the polynomial. Okay, so we are restricted to the regular graph. So if G is a regular graph on n points and m lines, then the Sommer polynomial means characteristic polynomial of the Sommer matrix. So Sommer polynomial of the semi-total line graph is this one if R is 1, and if R is more than or equal to 2, we will get this expression. We will get this plus in addition to that characteristic polynomial of G. This is adjacency polynomial. Okay, adjacency polynomial of G with this parameter. So if you know the adjacency polynomial of a graph G, you can get the Sommer polynomial of the semi-total line graph of G. Okay. Similarly, the Sommer polynomial of the semi-total point graph is expressed in this form. If R is 1, this is the expression. If R is more than or equal to 2, then you'll get this. So here also, knowing the polynomial, adjacency polynomial of a graph G, we can get the Sommer polynomial of the semi-total point graph. Okay. Then Sommer energy. So again, here also same in analogous to the ordinary graph energy. The energy of a Sommer energy is also sum of the absolute values of the eigenvalues of the Sommer matrix. So if R is 1 means you will get the matching, correct? So when for matching, the Sommer energy of T1G is 2m root 2, and for semi-total point graph it is 8m root 2. And if R is more than or equal to 2, okay, graph G with regularity is more than or equal to, then the Sommer energy of the semi-total line graph is given by this expression, and for the point graph it is given by this expression in terms of the adjacency eigenvalues of a graph G. Okay, this is a Nirmala polynomial. Again, here also similarity is there. In the Sommer index, we get a square root of du square plus dv square. Whereas Nirmala index, it is simply square root of du plus dv, where u and v are adjacent. Okay, so same technique is used for the can be used for the Nirmala polynomial also. Okay, because similarity is there, only square is not there. In the Sommer index, we get here square root of du square plus dv square. Here it is without square, means only simply square root of du plus dv, where u and v are adjacent. Then correspondingly matrix can be defined, that is called the Nirmala matrix. This is defined by and introduced by Gutmann and Coley. Okay, so it is also square matrix whose ijth entry is square root of d of vi plus d of vj if vi is adjacent to vj, otherwise 0. And the characteristic polynomial of this Nirmala matrix is called the Nirmala polynomial. Okay. So again, if G is a regular graph with n points and m lines, then the Nirmala polynomial of the semi-total line graph is lambda raised to n minus m, lambda square minus 6 raised to n. If R is 1, and if R is greater than or equal to 2, you will get this expression. Okay, and similarly for the semi-total point graph, we can get the Nirmala polynomial of the semi-total point graph in the form of a characteristic polynomial of a graph G with parameter this. Okay, so again here also knowing the eigenvalues of a graph G, adjacency eigenvalue of G, if you know, we can easily from this expression we can get the Nirmala polynomial of the T1G and T2G. Okay, then same way again, Nirmala energy, that is sum of the absolute values of the eigenvalues of the Nirmala matrix. So if R is 1, then the Nirmala energy of T1G is 2m root 6, and if and for the semi-total point graph it is 8m. Whereas R is more than or equal to 2, then the Nirmala energy of T1G will be given by this form, and the Nirmala energy of the semi-total point graph is given in this form. Okay. Now come to the Zagreb indices. So this is a one of the first index based on the degree defined in the year 1978 by Gutmann and Gymnastic. Okay, so first Zagreb index is defined as summation of square of the degrees of the point, which can be expressed in this form: summation of the degree of u plus degree of v, where u and v are adjacent. Okay, where u and v are adjacent, then the we can write degree of u plus degree of u. So sum of over all the edges is called the first Zagreb index. Similarly, the second Zagreb index is the summation of degree of u into degree of v, where u and v are adjacent. Here it is addition, here it is a product. Okay, so if u and v are adjacent product, that is called the second Zagreb index. So based on from these two indices, the other indices that came afterwards, that is Somber index, Nirmala index, Randick index, many more. Okay, so here we'll express some results on the semi-total graphs. So here, if G is a graph with n points and m lines, and vertex set is V of G, then the first Zagreb index of the semi-total line graph of subdivision graph. Okay, semi-total line graph of subdivision graph. Already results are done for the semi-total line, what you can say, semi-total line graph and any graph and like that. And then particular cases are done. Then we generalize this for any graph. Okay, the semi-total point graph, semi-total line graph of the subdivision graph is 12m plus 5 into first Zagreb index plus summation of dv cube. Okay, and the second Zagreb index of the T1 of SG is given by this expression. So if we know the Zagreb indices of G, okay, and the degrees of vertices, one can get the Zagreb indices of the semi-total line graph of subdivision graph and semi-total point graph of subdivision graph. Okay. Then if G is a graph with n points, then the Zagreb indices of the semi-total point graph is given by this. Simply see, it is a very linear relation: 24m plus 4m1g, and second Zagreb index of semi-total point graph of SG is 16m plus 12m1g. Okay, here it is not that easy. Expression is not that simple, but here directly in terms of m1 only, we can get the Zagreb indices of the semi-total point graph of subdivision. Okay, co-indices. Co-indices means taking the summation or non-adjacent pair. Okay, so m1 bar is a summation of degree of u plus degree of v, where u and v are not adjacent. In Zagreb index, we take here adjacency. Okay, adjacency. U and v must be adjacent. Then only we can write this summation. In co-index, we'll take they are not adjacent. Means the edge uv is not there. Okay. Similarly, the second Zagreb, this Zagreb co-index is degree of u into degree of v, where u and v are not the adjacent points. So Gutmann give the following results in terms of Zagreb indices and the co-indices of graph. So if G is a graph with n points and m lines, then the m1 bar G is 2m into n minus 1 minus m1g, and m2 bar G is 2m square minus half m1g minus m2g. So knowing these results, we can get, and already we know the results on the Zagreb indices of the T1 and T2. Correct. Zagreb indices of T1 and T2 we know. Okay, and using these results, easily one can write the Zagreb co-indices of the T1 of SG and T2 of SG. Okay, so from that we can see if G has n what is m, then easily T1 SG has n plus 3m points and these many edges, that is 4m plus half m1g, and T2 SG has n plus 3m vertices and 6m edges. So knowing the number of points, knowing the number of lines, and then m1, m2s, we can write the Zagreb co-indices of the T1 of SG and T2 of SG. Okay. So see here. So let G be a graph with n points, m lines. Then the Zagreb co-index of T1 of SG is given in this form. Second Zagreb co-index of T1 of SG is this form. Similarly, the Zagreb co-index of semi-total point graph of subdivision graph given in this form. Okay, so these are the few references. So these are the, as at the beginning I told, these are the three papers in which Sampath Kumar and student elaborated the basic results on the semi-total line graph and semi-total point graph. Okay, thank you.
Thank you, Professor Ramani, for such a nice presentation. It was a real tribute to Professor Sampath Kumar, since you have started right from the semi-total graph, which has been introduced in 1973. And from there, you have shown how the topological indices, energies of these derived graphs are found.
Yeah.
So we are thankful to you very much. Now I would like to ask the audience if they have any questions.
Okay.
Hello.
Yes, ma'am, please.
Hello.
Yes, good evening to all of you.
Yes, good evening, ma'am.
I would like to add on the topic which Professor S. Ramani worked. I said I have given that talk and also he has worked further. Semi-total graph of a graph introduced by Professor Sampath Kumar, one of the students. So as far as semi-total graph of a graph and as a total graph of a graph are concerned, my student Deepa Sinha, one of our students, Praveen, they have two papers on, because for semi-total graphs, they introduced semi-total sign graphs.
Okay.
And similarly, I think the total graph of a sign graph was also introduced. So on these two papers are some results of semi-total sign graph by Deepa Sinha and Praveen Garg, which is published in 2011.
Okay.
And one more paper, characterization of total sign graphs and semi-total sign graphs, that is also worked by Deepa Sinha and Praveen Garg. What I want to emphasize, the concept of semi-total graph, which was introduced by Mr. Sampath Kumar, I think, way back in 1973, how it is expanding, okay, within the realm of sign graphs. And those who are interested in sign graphs of a new generation, they may look into these two papers and take up his results, which hold for graphs, to see them in the realm of sign graphs.
Sign graph, correct.
Thank you.
Yeah. It is very nice, ma'am, for the young generation to see those results.
Yes.
Whether it is applicable for the sign graph or something new can be done.
Yeah, something always this thing can be done, and actually the definitions given by Deepa and Praveen, I feel it can be extended
Okay.
in a different setup,
Okay.
which has not, because as far as the line graph of a graph is concerned,
Yes,
there is a concept of line sign graph introduced by Behzad and started long back. And on that one, we do have on line sign graphs. So we have myself and Deepa and myself. We have papers. Because in the as far as the line graph is concerned, we have only one definition.
Okay.
When we go to the sign graphs, because lines also have the sign and verses also have the sign. With respect to the adjacency and the product, or I think we can have we have introduced, I have introduced myself and Dr. Acharya. Line sign graph is already introduced, and we have a product line sign graph as well as the dot line sign graph.
Okay.
So these results on semi-total graph, semi-total graph of a graph with respect to product line sign graph as well as the dot line sign graph has not been seen present.
Okay.
So
thank you, ma'am.
Yes.
Thank you very much
for adding some new ideas.
Yes.
Sir, I have just a small query.
Okay.
Regarding that degree subtraction adjacency matrix.
Okay.
As you have mentioned, that has become a skew symmetric matrix since you have taken Dij as the degree of the ith vertex minus the degree of the jth vertex.
Yes, yes,
And the advantage of a symmetry matrix is that the eigenvalues are real. So that advantage has been lost here. Some
Yeah, yeah.
eigenvalues may be
Yeah.
imaginary also.
yes, yes.
That you have mentioned.
Yeah.
Sir, instead of that, if we have taken the difference, that is absolute value of degree of I and the degree of j vertex, would
Yes,
the
sir.
results be
Yes, sir.
different?
Yes, results will be different, and already some results are obtained on that also.
Oh, that has also been
Ah.
done by
Means they are mentioned difference. So you take modulus of the d of vi minus d of vj.
yes, sir.
Yeah. So in that case, it will be symmetric matrix.
Yes.
Okay.
Okay, thank you, sir.
Dr. Naik, hello.
Huh.
Hello,
Yes, sir.
there are two questions in the chat box. See your message box.
Okay.
So someone, could you please read out the questions sent by the audience?
Yes, sir. So I'm checking.
What the meaning of DSA energy?
So I have one question. What is the use, purpose, and application of Somber index?
Okay.
This is question from Nanda Kumar. The name is there. Okay. So please.
Okay. Somber index is defined at par with the Zagreb index and all that. But the difference is that they are given the geometrical approach, because it comes to square root of du square plus dv square. So they took as a distance from the point here du dv to origin in the xy plane. Okay. And these indices, they are applied with the properties of some chemicals, and they have got that means they are observed that the prediction value of this indices is more than the other indices. Okay, is it clear? Hello.
Yes, sir. So there is no other question. So
There is another question. What is, just I have read out the question. Okay. So Priyadarshini asks another question. What is DSA energy?
What is the DSA? That is degree subtraction adjacency, the sum of the absolute values of the eigenvalues of DSA matrix. So it is just similar to the ordinary energy. Ordinary energy means energy of the graph, which is defined with respect to the adjacency, means eigenvalues of the adjacency matrix.
Okay. Okay, there is no more question. So, Dr. Naim, you conclude the session.
Yes, sir. So thank you very much, Professor Ramane, for your nice presentation and all the clarifications. So thank you once again for being with us.
Okay.
Thank you very much, Professor Ramani, for your excellent presentation.
Thank you, sir.
Over.
okay. Thank you, Professor Ramane, for the nice presentation, interactive. Thank you, Professor Abu Noin, sir, for your time. This is the end of session 1. I would like to request Srinanda to continue. Thank you.
Thank you, Dr. Shamanto. After the successful completion of first invited lecture session, I would now like to welcome everyone to our second invited lecture session. The speaker for this session is Professor Ankur Bharali from Dibrugarh University, Assam. The session will be chaired by Professor H. Ramani, and I would now like to ask Dr. Akul Rana from Narajol Raj College, West Bengal, India, to be the session coordinator.
Thank you. Thank you, Srinanda.
Welcome, sir.
Hi, everyone. Welcome to the lecture session 2. In this session, we have with us Professor Ankur Bharali from Dibrugarh University as the speaker, and Professor H. Ramane will chair the session. Now, here is brief introduction of Professor Ankur Bharali. Professor Ankur Bharali is a professor of mathematics at Dibrugarh University, Assam, specializing on graph theory and complex networks. He earned his MSc from IIT Guwahati and holds a PhD in mathematics from Dibrugarh University. Professor Bharali is the director of the IQAC and oversees the Center for Distance and Online Education at Dibrugarh University as the director of CIQA. Additionally, Professor Bharali is currently serving as the chief editor of Mathematical Forum, a UGC care-listed journal. In the past decade, Professor Bharali has completed 2 research projects and published over 40 research articles and book chapters in various reputed journals. He has received several prestigious fellowships, associateships, and international travel support from UGC and served DST to pursue his research. He supervised 11 PhD and MPhil scholars, contributing to their successful completion of degrees. Professor Bharali is also involved in numerous academic and quasi-academic bodies and committees within and outside the state of Assam. We are grateful to Professor Bharali for accepting our invitation. Professor Bharali will talk on an excellent topic, adjacency-like matrices of diagram. The session will be chaired by Professor H. Ramane. Now, without delay, I request Professor H. Ramane, chairman of this session, to take the charge of this session. Up to you, Professor Ramane, please.
Okay. Thank you, sir. Thank you. Once again, I welcome all of you for this second session, and the speaker is Ankur Barli. And I request Ankur Barli to please deliver his lecture.
Thank you, sir. I am really happy to be here in this particular workshop, and it's my honor to present when in the chair is Professor Ramane. Thank you, sir. And I can see many familiar faces: Professor Paul, Dr. Naim, and many other people working in the theory of graphs. First of all, I'd like to thank the organizer for inviting me to this workshop. So the topic that I have chosen for this particular workshop is the adjacency-like matrices. I'm trying to keep it in a very general perspective rather than from the perspective of the students or researchers of graph theory. So it will be like very introductory in nature. Then as the talk progresses, we'll try to see some of the critical aspect of this particular topic. So let me share my screen. Excuse me, I'm having some issues. Excuse me.
I think he has left.
There may be some technical issues. Shinanda, can you call Professor?
No, most probably any technical problem has been reached.
Just call him.
Is it visible? Hello,
Yeah, it's visible from my end.
Yes, sir,
audience.
visible.
Yes, sir, it is visible.
Okay.
Okay, anyway,
So,
sorry for the trouble. We have lost a couple of minutes of time. Let me start the presentation. Is it possible to make it the full screen?
1 minute. You start, just to start.
Yeah. So basically, when we talk about the matrix representation of graph, usually we have some numbers associated with the edges, and for some the non-adjacent vertices, we usually put 0 against that. So the traditional adjacency matrix that we have is 1 when we have an edge and 0 when we have. It's okay, sir. Thank you. Yeah. Yeah. Next slide. Next. And can be generalized to weighted graphs also, where the weights of the edges will come up when in place of 1, and when there is no edge between a pair of vertices, it will be 0. So that is the whole idea of having an adjacency matrix or the weighted adjacency matrix. Now, with the yes, okay, with the study of the topological indices, there comes the question of defining the defining matrices which are analogous to the traditional adjacency matrix and which can represent the spectral property of a particular topological index. So this is an example of a very a traditional adjacency matrix where we put 1 for an edge and 0 for when there is no edge. Okay, and if there is some weight on the edge, so instead of 1 we will put that particular weight. So this can be generalized to, so can you go to the next slide? Next. Yeah. So here you can see that this can be generalized to a function of the participating vertices for a particular edge. So instead of putting 1 or some arbitrary weights or the weights which are there in the edge, we can define a function that can be a function of the vertices participating in that particular edge. And the matrix that will obtain with this definition, that will be then studied, and the eigenvalues and their multiplicities will be obtained. For the adjacency matrix, we call it the spectra of the graph, the entire thing, the indices, the eigenvalues as well as their multiplicities. With the upcharge of the topological, as Professor Ramana has already mentioned, that this is a very popular topic. We have thousands of topological indices defined based on various geometrical biological characteristics, based on their prediction ability, based on the graph parameters like degree, distance, status. So there are a lot of topological indices which are being studied over the last couple of decades or so. It was introduced actually by Wiener in 1947. It was not a degree-based topological index, it's a distance-based topological index. And as Ramana sir has already mentioned, that it was the Zagreb index, which is considered as the first degree-based topological index. And based on these indices, next slide, sir. So these are some of the applications of or the significance of TIs. They can be used as the molecular descriptors. They can be used as used in predicting physicochemical properties. They are being utilized in drug designing and so on and so forth. So based on these indices, what we can do is that, so the general form of these indices can be the sum of I is adjacent to j, f of di dj. So f of di dj is a function of the degree. So now this function can be incorporated in the weighted adjacency matrix. So this idea is very simple. So corresponding to, say, for example, Randic matrix, Randic index, we have f di dj is 1 by square root of di dj. For first Zagreb index, f di dj is di plus dj. For second Zagreb index, f di dj is equal to di dj. So corresponding to this, we can define the matrices. And these are basically called the large bracket. The whole spectrum of this kind of matrices are in the class of adjacency like matrices. Now we have come up with some other generalizations also, like A alpha and all, but these are the adjacency like matrices based on topological index. You see, the idea of defining these analogous definitions are not always for some practical purpose. Some of the parameters are defined just as graph parameters. They are being studied and pursued as graph parameters without being considering their practical application. But yes, if there is some practical application, we always welcome that particular definition, and we always, it will become a different level of popularity, of course. So corresponding to the Randic matrix, corresponding to the Randic index, this Randic matrix was defined, Rodriguez and all, in 2005. They have also defined the geometric arithmetic metrics, and so on and so forth. Later it was Borjak who defined or who studied this further. Then we have first Zagreb index, second derivation already discussed by Ramana sir, and which was proposed in 2018. Then in 2018, Chan proposed, this is called ABC index or atom bone connectivity index. We have defined in 2020 inverse sum in degree index, ISI index. And now, so the objective of this particular lecture is to take this idea forward to the directed, or what is called a mixed graph. So what is the difference? The slightest difference, as we probably all know, the slightest difference is that when we have a directed graph, there will be no undirected edges. When we have a mixed graph, there may be some undirected edges also, along with some directed graph. So mixed graph, you can say it's a generalization of the directed graph also, right? So there will be two directions. One, just during the Q&A session, Dr. Naim was suggesting or querying one thing is that where we are going to lose the advantage of having real matrix, real eigenvalues. Say, for example, if we define a skew matrix for a directed graph like this, where one direction is considered as 1, the other direction is considered as -1, we end up getting a skew matrix, and we all know that the eigenvalues of this matrix will be non-real. So that is one issue that if we want to overcome, what are the chances of it? So for a real matrix to define a directed graph properly, at the same time having real eigenvalue is not easy. In fact, it is not yet done. So what we have done, or what the researchers have done, that they have changed the entries of the matrix to complex. So either you stick to the real entries and get some complex eigenvalues, or you can go to complex entries so that you can have a Hermitian matrix and you'll get the real eigenvalue. So this is the whole idea. And here you can see the one important question that I have already mentioned, that can you obtain a matrix with complex entry? Because for real entry it is not possible, which can generate a real eigenvalue. And for mixed graph, what will be the generalization? So these are the questions in place. In Go and Mohar has introduced this Hermitian adjacency matrix using the square root of unity as the entry for the directed edges. If it is from, say, di to dj, then the ij place will be, say, I, and ji place will be minus I, so on and so forth. So again, we have a Hermitian matrix and we'll get a real set of eigenvalues. So this is the matrix which was further studied by Liu and Lee, and also discuss some application of this matrix in mathematical chemistry. Later in, or you can say recently in 2020, actually, B. Mohan come up with another choice for Hermitian adjacency matrix. So he suggested that instead of using I and minus I, what we can do is that we can use the sixth root of unity. And he also argued that this can be a more natural choice because of the fact that when we add I with minus I, we'll get 0. But when we add omega with omega bar, we'll get 1. So what he has suggested is that for one direction, we'll have omega. For the other direction, we'll have omega bar. So this matrix is known as the Hermitian matrix of second kind. Again, being a Hermitian matrix, the eigenvalues are all real. Now, let me, or later I will try to convince you why this particular combinatorial property, that the sum of I and minus 1 I is 0 and omega I is 1, is going to play a key role in having some very specific result. So this is the first adjacency matrix that we have, Hermitian adjacency matrix, and this is the Hermitian adjacency matrix of second kind. So difference is that you will have 6 root of unity in place of square root of unity. So in 2017, Liu et al. Has defined this Hermitian Rendik matrix. So what they have done, they have extended the idea of Hermitian Rendik matrix, or they want to obtain an analogous Rendik matrix for the mixed graphs. So if there is no direction, it is just like the Rendik matrix. But if there is a direction, we have to consider one to be I by square root of di dj, the other one to be minus I square root of di dj. So this is the whole idea of defining this Hermitian Rendik matrix. Of course, it is basically for a mixed graph. And recently, this is what we come up with, that we have tried to have a similar matrix based on the Rendik matrix of second kind, and we defined it as Hermitian Rendik matrix of second kind. So this is the matrix. In place of I, we have omega and omega. And let us see that what are the changes or what are the difference that you can have if we define this matrix like this. So this is a list of various matrices associated with undirected to mixed graph. I'm just listing them so that you can have an idea that these are the analogous kind of definition, starting from adjacency, the generalization, or you can say the adjacency matrix like matrix with respect to the Rendik matrix, Rendik index is the Rendik matrix. Then we have Laplacian. There is a relation between Laplacian and this Rendik matrix, and so on and so forth. So ultimately, we have the last one, the last the table. You can see that this is what we did. Okay, so now I'm highlighting one result from the number of cycles that is going to decide the determinant. Right. So this is for Randic matrix when we use the idea of the first Hermitian. Okay. Then can you go to the next slide, sir? So here what we have done is that we have to define some analogous definition. Say, for example, we come up with this semi-positive notion where this omega and omega bar. So otherwise, this is like in earlier case, this is like I and minus I, 1 or minus 1. So based on that, you can just figure it out what will be the positive and semi-positive cycles. Here we define semi-positive cycles as omega and omega bar without any negative sign. For the other one, we will have negative semi-cycle. And then here you can see that the determinant after this kind of manipulation and you can say alteration, we come up with this formula for determinant. Here you can see that the number of positive, negative, semi-positive and semi-negative cycles, all the cycles of 4 kinds are actually playing a role in finding the determinant. Why this is happening? Because you can see that if I have in one cycle, if that the value of the cycle is I, if the value of the other cycle is minus I, then they will basically get cancelled when if I sum them up. But in case of the second kind, we have omega and omega bar. If I sum them up, I will get +1. So this is what the Mohr has suggested, that if we have this omega plus, since we have omega plus omega bar to be equal to 1 rather than I plus minus I is equal to 1 is equal to 0, this will give us an advantage in defining many other combinatorial property in the graph. So this is one example where we have found that this particular notion or this particular idea is playing a very key role. Next slide, sir. Similarly, here also ILN, LSN, LP, LN, all these are actually coming into picture. And the summation is here, the summation is taking over all elementary subgraph rather than only real elementary subgraph. This is a very significant change. Earlier in the first result, in the result proposed by Liu in 2017, they have summed up for only real elementary subgraphs. But now we have considered all possible subgraphs, all elementary subgraphs for this particular result. So that is the difference. And these are some of the corollaries you can say for if it is a tree, what will happen? And if the underlying graph is regular, what will happen? So these are some results from the polynomial. Right. And in 2020, Kannan has proposed this graph in connection with gain graph. I don't want to go into detail of gain graph because I see that in the next session, gain graph will be discussed in at length. So I just want to show that this result has some connection with the gain graph, and for our matrix, this will be something like this. So the next result is very interesting. The spectra of lambda, that second Hermitian Randic matrix, the spectra lies in between -1 and +1. So this is a very interesting result. The next one is that if X is a positive matrix, positive graph, and 1 is simple eigenvalue for the second Randic Hermitian matrix. And if it is bipartite, we have got that this is symmetric about 0. The spectra is symmetric about 0. So these are some of the results which are more like the results that we have in our traditional case. But these results were not possible, or possible, but there are some differences in the traditional result and in the results found by Liu in 2017 with the definition of the first Hermitian Randic matrix. Okay. So this is another result. This is you can say it is an interlacing properties basically. So if you reduce one edge or if you delete one edge, what will happen to the spectra? So here you can see, I just, sir, can you go to the next slide? So I just give you the sketch of the proof. So here you can see that the next slide, sir. So 1 minute, so these things are very familiar, I think. These things are very familiar. This is Rayleigh quotient, and these results are basically very familiar to us. The next slide, sir. So here you can see this is nothing but this current feature theorem, and there this is the Rayleigh quotient. Then you can have the max spin formula for lambda k. And the next slide, what you can see is that there is an additional condition required. That is square root of d2 x1 is equal to h12. That is basically the entry in the matrix. Square root of d1 x2. So the x that will be an eigenvector for the next eigenvalue should possess this particular condition. So this condition has to be included in the max min formula, so that we can have a result for lambda k plus 1. So here you can see that this particular result, square root of d2 x1 equal to h1 to square root of d1 x2 is actually being translated to an orthogonal condition. So what is the orthogonal condition? The condition is that x will be perpendicular to this vector. So this is a modification of the standard vector. E1 is basically 1 in the first place and 0 elsewhere. E2 is 0, 1 and 0 in the rest of the positions. So these two standard basis vectors are there, based on which we have defined the x, or we condition the x such that x has to be perpendicular to this vector. And this condition of equality, that square root of d2 x1 is equal to h1 to square root of d1 x2, this condition is now being replaced by this orthogonal condition in the next slide. So can you go to the next slide? So if you replace that particular condition, then we'll get the result. So this is the idea based on which we can obtain the result. Now, an application of this spectral theory. So as we all know that energy is what was proposed by Guttman in 1978. It is the sum of the absolute value of the eigenvalues, and these eigenvalues are the eigenvalues of the adjacency matrix. And analogous to this, we have several definitions. And for this Hermitian Rendik energy of second kind, we have adopted a similar approach, and the eigenvalues obtained from this Hermitian Rendik matrix of second kind, we use them to formulate the energy. These are the results that we have obtained. Here, this energy will be bounded by these two parameters, where r to the power minus 1 xu is the underlying graph. Xu is the underlying graph, and r to the power minus 1, this is basically coming from the generalization of Rendik matrix, where alpha is equal to minus 1, just mentioned in the last slide. And this is the result. This is another result, which is basically a lower bound and a relation between the energy and the determinant. This is another result, which is an upper bound. Sorry, sir. Sorry. Am I audible?
Yes.
Yes, sir.
Yeah. So what is the future direction? What is the future? So what is the future direction of this particular topic? The future direction of this particular topic is, I mean, there are many directions where we can move based on various, as Sir has also already mentioned, Ramana Sir has already mentioned, that based on SOMBER, we have defined SOMBER matrix. So for any index, we can always define a matrix. But here the direction that I want to discuss about, so can you go to the last slide? Is that where the weights of the graphs will not be scalar weight. The weights will be now matrix. So this was first proposed by Bapat in 2006. It has gained popularity in 2019 and late in 2020. So now the weights are no longer scalar. We will have some matrix weight. These matrix can be semi-positive definite matrix, and usually they are semi-positive definite matrix, but we may have some other matrices as per our convenience. We can define, and based on that, we can explore what are the consequences of the spectra. So with this, I want to conclude. I'm very sorry that my internet connection is not working properly. There are some issues, and sorry for the disturbance. Thank you. Thank you, sir. These are my references. So this paper was just accepted in Journal of Algebraic System. You can check the 4th paper. So this, we have proposed this Randic matrix of second kind in this particular paper. It's a joint work of me, my student, and one scholar from IIT Guwahati. He is Vikas Bhattacharya. And we have proposed the ISI index, which is mentioned in the 3rd reference. And there are some other references also. Thank you. Thank you, sir, for your opportunity. Thank you, organizer. If you have some query, I'll be happy to answer.
Any questions or anything from the audience? No questions. Ankur sir, I have one doubt.
Yes, sir.
You told in one of the slide that eigenvalues lies between only in -1 and +1.
Yes, sir. For this particular matrix.
For which matrix it is?
The matrix that we have proposed, this Randic Hermitian matrix of second kind.
Okay.
Sir,
For
because of the denominator term, no? The square root of Dij, that is playing a key role to keep it in between -1 and 1.
Okay. So for any graph with any for that matrix.
Yes, so that's why it is interesting, I think.
Yeah. It's very nice one.
Yeah.
And is there any kind of this, for example, a mixed graph? Okay, some lines will be directed, some will be undirected. Okay, whether you observe anything or something, or I have done means converting all the directed edges in the form of a simple edges, and then the simple edges in the form of a directed, or something can be like
Okay,
just like in the switching we do direction we can change even though the spectra remains same there.
Yeah.
So here it is.
Oh, I haven't tried that particular. Yes.
Okay.
Definitely it will be interesting. Yeah.
Switching to the directed to the undirected like that.
Yes.
It is generally happens, no? The undirected edge can be replaced by two directed
Directed also.
in opposite directions. So the entire graph becomes a directed one.
So in that case, say for example, in our earlier matrix, in Randic matrix, we have I in one direction minus I in other direction. So if I add them, I'll get 0, no edge. But now we have omega and omega bar. So the
Ah,
sum will, so that is the combinatorial trick
Yes.
actually.
Yes.
Yes,
yes.
Professor Paul has rightly pointed out. So this is
Mm.
an easy example to understand the combinatorial idea.
Mm.
Why we have defined this omega and omega bar
Mm.
instead of
Mm.
I and minus n.
Mm.
Thank you.
Yeah.
So there is one question from the audience.
Yeah.
Say, what about applications?
Yes.
Generally, you have input set.
So there is a
Any
nice
particular
paper.
research? Okay.
Yes, there is a nice paper of Gutman and Fortula that was proposed, that was published in AKC, I guess, in 2018.
Yeah.
It has established, yes, some relation with Rendic energy with the information
Mm.
index or
Mm.
something like that. So that paper was very extensive, and it has discussed in breadth. At breadth, they have discussed that what are the possible applications of Rendic energy in computer science or in theory of electronics.
So another question, similar thing, physical significance.
When I think of physical significance, I don't want to conclude anything here only. But yes, there are some indices which will have these advantages, because you see, in case of Rendic index, if you consider a Rendic index, it is just like the normalized Laplacian index, and we have seen a lot of physical applications of Laplacian and normalized Laplacian index. So there is a similarity between the Rendic index, Rendic energy, with the normalized Laplacian. So I think in that direction you can think and you can explore.
Okay.
Any more question from audience?
I think it is not there. So, so if there is no any further questions, let us conclude. I thank Ankur Barli. Nicely, he has given the adjacencies like matrices of the digraphs and mixed graphs and everything. Because nowadays, earlier only the adjacency matrices.
Sir, there is another simple question. Please mention some research opportunities in topological indices. Research opportunities. No?
Okay.
We can define different type of your topological indices.
Yeah.
But the author should find out what is the application of this kind of indices. So it is my observation.
Yes.
So that so based on the function f of di dz, so by choosing appropriate functions, appropriate value of the function, we can define lot of different type of your topological indices. But if it has some application, real application, then it has some significance. Otherwise, there is no significance.
Right. It is just the fun, just for fun only. If there is no application.
Yes.
Yeah.
Okay.
I also like to thank the organizers for the initiative. The academy is, I think this is the first award.
Yeah.
So I wish them best of luck in the coming days,
Thank you.
and hope to meet you again.
Sure.
Thank you.
Okay, sir. Thank you. Ankur
And once
Barli.
again, sorry for my internet.
No, it's okay. Because it happens. No problem. No issues.
Yeah.
Okay, so nicely he has given the adjacencies like matrices, and he narrated many things, especially that Hermitian matrices and its properties from I to again W and all that omega. So there is a lot of scope to work on such concepts. Not only Randic, he has mentioned Randic. So there are so many indices from index to matrix, from matrix to index. One can look into all the directions. So there's a lot of scope in the such area, especially for the youngsters to look into this. So thank you very much, sir, for nicely giving the lecture. Thank you very much. I thank the organizers for giving me opportunity to chair this session, and I hand over it to the Dr. Sukumar.
Thank you, sir. Shannon, please continue, ma'am.
With that, we have completed our invited lecture session 2. And moving on, we are to proceed with our third invited lecture session. The speaker for this session will be Professor Shahul Hamid K, Principal of Government Arts and Science College, Uduma, Kerala. The session will be chaired by Professor Ankur Bharali, and I would now like to ask the session coordinator, Dr. Shukumar Mondol, To carry on with the session, he is the Associate Professor of Raja NL Khan Women's College, West Bengal, India. Sir, please.
Thank you, Srinanda.
Welcome, sir.
Okay. It is the time for invited lecture number 3. So I am lucky, and it is my great pleasure that I want to introduce an eminent mathematician who is the speaker and who is working on the graph theory. Now I request also Professor Ankur Bharali to take the chair as the session chairperson. Now I want to introduce before lecture the Professor Shahul Hamid K, Principal, Government Arts and Science College, Uduma, Kasaragod in Kerala. His teaching experience is more than 30 years in various government colleges. His research interest is mainly in spectral graph theory, dealing with such discrete structure like sine graphs, gain graphs, and skew gain graphs. He has published more than 25 research papers in reputed journals, and 6 research scholars are now currently working under his supervision. He is associated with several journals as their reviewer. He has presented several talks in national and international conferences. So I request Professor Shahul Hamid K, whose topic is conjugate skew gain graphs and their applications. Now I request Professor Ankur Bharali to take over the session as the chairperson of the session.
Thank you, Dr. Mandal.
Thank you.
Thank you, organizer, for this opportunity. I would like to request Professor Shahul Hamid K. Sir, please share your screen. He is going to speak on conjugate skew gain graph and their applications. Sir, please share your screen. Yes, it's visible now. Right. Okay.
Am I audible?
Yes, yes. Perfect.
Okay. Thank you, sir. I'm using a mobile, so the screen presentation may not be that much perfect.
It's okay. It's
Is it visible now?
Yes, yes, yes.
Okay. Okay. I must first of all thank Professor Madhumankal Pal for inviting me to this great webinar in memory of beloved Professor E. Sambat Kumar. Before I begin, I must say a few words about this legend. When I started working in the field of graph theory, I had the opportunity of meeting him on several occasions, of course, in various seminars and all. What I noticed in him is the extra energy with several features with curiosity that is it okay? Audible?
Yes, yes, yes.
Screen is visible also. Net connection here also is a problem.
Yes, yes.
Okay. With curiosity, just like a child, even at that age, he was listening to many lectures of youngsters, and he is encouraging all these youngsters to go into serious, deeper research, and that's how I reached here. So at the start of my research, he helped me a lot, so that I must remember at this moment while we commemorate, while we have a seminar in his honor. So today, I have the opportunity of listening to the former speaker who is now chairing, Professor Ankur Barali. But unfortunately, I had to leave while Professor Ramani was speaking. So that was a misfortune as far as I'm concerned. Anyhow, let me share my screen. Here is the topic which I will be discussing today. It is about conjugate skew gain graphs and their applications. Professor Ankur was discussing about mixed graphs in the previous lecture. And in a similar way, we can have instead of that omega bar I and minus I, my structure, conjugate skew gain graphs, will be the one where you can use any complex number. That is the advantage we will see here in the adjacency matrix or Laplacian matrix that we are going to see. Okay, this is the second slide. Is it visible?
Yes, sir.
Okay. Outline of the talk. I will first introduce these three structures: sine graphs, and then finally skew gain graphs. A particular case of skew gain graphs is what we are focusing today. It is conjugate skew gain graphs. So skew gain graph is a much larger extension or generalization of graphs, sine graphs, and gain graphs. And of course, from the skew gain graphs, we have selected a particular case where we can find some applications of that conjugate skew gain graphs to the realm of social balance theory or sociology, mathematical sociology, so to say. Now, after that, I'll go on to some matrices associated with these graphs. Then I will introduce new operations on matrices with which we can have what is that relation that usually connects with Laplacian and incidence matrices. Then we will have G Laplacian matrices for skew gain graphs. Matrix P theorem will be mentioned without giving the detailed proof. Then we will have the final conjugate skew gain graphs discussed at length. So already this is known to you. Graph is something which is a pair consisting of vertices and edges. Of course, as we are dealing with simple graphs where many of the So sine graph is something general to that is graph. It is a ordered pair G sigma, where G we call it as the underlying graph, and sigma is the signature on edges, assigning +1 or -1 to the edges. So step by step we'll move. This is the next level. Gain graph is a further extension of sine graph. A gain graph, we require three things here. We require orientation also. In the case of sine graphs, you can see this set +1, -1 is a multiplicative group. So replacing that multiplicative group by a general group gamma, and instead of this notation sigma there for sine graph, we use this P symbol or phi, whatever it is. This one that we call it as gain function from the oriented edge set. Oriented edge means for an edge, say UV, we'll consider some kind of direction is there, but it's not a directed graph. If we have an edge UV, we'll have to consider VU also. But whenever we assign something on the edge UV, the other one is implicitly obtained using the last relation phi P of VU, the oriented edge VU, will be having inverse. So that's a peculiarity of this gain graph. So in the case of sine graph, what happens is +1 and -1 are self-invertible. So inverse does not be, the orientation do not matter. So here in the case of a gain graph, and from now onwards, we require a prescribed orientation for assigning this weights on the oriented edges. So for an edge UV, we'll have another corresponding pair VU also, but in the other direction. And assigning a weight on that from the group, we will use this formula phi of VU. Means if we first assign the value phi of UV, in order to get phi of VU, we'll have to take the inverse. So this is how gain graph is defined. Now moving ahead, we'll have to see what the kind of things are, we call it as skew gain graphs. Before having that, we require one more thing which we have to define: anti-involution or anti-involution. If we have an algebraic group gamma, a function f from gamma to gamma is called an anti-involution. If f of xy is fy into f of x, usually you might have seen the case of algebra, xy inverse is y inverse, x inverse, such kind of thing. So that is the inverse is there in the case of gain graph. We can see that skew gain graph is something which generalizes this idea of gain graphs. So such a function is required, f from the group to the group itself. And the second one is very important, f of x must be x. So we call such a function as involution. So the sense of anti-thing is anti-automorphism must be there. If f of xy must be equal to not f of x in the f of y, it must be f of y in the f of x. If the group is abelian, usually we take abelian groups, so then it will be simply homomorphism or automorphism. Okay, these are some examples of anti-involution. What I want to say here, especially for the new researchers, while dealing with conjugate skew gain graphs, we have taken that function as f of z equal to z bar. That is there in the example C. So let me begin with the first example. If gamma is a group, an algebraic group, the identity function f from gamma to gamma is f of xy be function is changed. It is now phi zeta, and the group remains gamma, and the function f also remains the same. Okay, as usual, this is how the adjacency matrix of a skew gain graph will be defined. If we have it as n vertices are there, and if you are given a skew gain graph, then you can have an n by n matrix Aij, where the ijth element will be phi of Vi Vj if Vi is adjacent to Vj. Of course, there must be the orientations to be taken. So, the first vertex will be called as a tail of that edge Vi Vj. If the tail is Vi and the edge is the head is Vj, then you must take that the weight from Vi to Vj as phi of Vi Vj. If they are not adjacent, you will have it as 0. But remember that if you have fixed it as Aij, then Aj will be computed with the help of that f Aij. So when it is gain graph, f Aij will be Aij inverse. When it is sine graph, as I told you, it will be Aij inverse is same as Aij itself. It is self-invertible. And generally, if it is, see later we'll be dealing with conjugate skew gain graph, then it will be Aij bar, whole bar, means complex conjugate. Okay, if you want to read more, these are the two papers which we published. First one in Southeast Asian Bulletin of Mathematics, with the title On the Characteristic Polynomial of Skew Gain Graphs, with me and my guide, Sis Jamina and others, her students. The second one is in Electronical Journal of Graph Theory on two Laplacian matrices of skew gain graphs. Basic papers of skew gain graphs by two computer scientists. I'll give you the references later. And only after that, after several years, matrices are assigned to these structures by us, by me and my guide and others, Roshni and all. Now, let me move on to conjugate skew gain graphs. Yeah, this is one of the papers. Only two papers are published for the time being. This is the first paper. We have extended the notion of balance theory to the class of conjugate skew gain graphs. It is published in Communications in Combinatorics and Optimization. It is there available online. Okay, as already mentioned, conjugate skew gain graphs are nothing but a particular case of skew gain graphs where the if you want to reverse the orientation and if you want to assign on the reverse the other way part of the edge, then it will be conjugation. That's all. So here the gamma will be taking the group as C times or the multiplicative group of complex number. And the notation for conjugate skew gain graph, we'll take it as G phi, because here F is not important. F is fixed. F is actually conjugation. So that's why we call it as conjugate skew gain graph. So this is an example where you can assign, see the beauty, we can assign any complex numbers, non-zero complex numbers on the edges. If you see the edge V1, V2, if you take it as an oriented edge, then V1 to V2, it is 1 plus I. Then from V2 to V1, it must be 1 minus I, its conjugate. That's how it is done. So this is how we deal with conjugate skew gain graphs. When it is a gain graph, it will be 1 by 1 plus I, it's inverse. But here conjugate skew gain graph, it will be 1 minus I. See, there is another idea which I want to mention here. There are several papers published by eminent mathematicians, especially in India, see about complex unit gain graphs. One is famous paper by Nathan Graf, a student of Professor Thomas Zaslavsky. You can read it, spectral properties of complex unit gain graphs. Complex unit gain graphs means it is not in the entire plane, it is there in the, see, we take that group as the T, means torus group, the units circle in the complex plane with set of all z such that mod z is equal to 1. So the modulus there will be 1. Okay, so here we can have any complex numbers. Yeah, in order to move towards the application, we require this very important definition, conjugates Q gain of a cycle. So whenever a cycle is there, say C-oriented cycle means, suppose the cycle is having the initial vertex V0, second vertex is V1, etc., going back to V0, N in length, then the edges, oriented edges are V0, V1, V1, V2, Vn, V0 with that prescribed orientations. Then you just take that product, then we call it as phi of C, that is phi of C in that direction. When you take the other way direction, that means the backward direction, it will be conjugation. That you know, the conjugate of the product is product of the conjugates. So that has to be kept in mind while dealing with balance theory that I will be referring to as an important application of this conjugate Q gain graphs. Am I with you?
Yes.
Okay. Let me proceed. Because I can't see the other screen. I'm just watching my mobile. Only the presentation is shown to me. Okay. So as I just mentioned, we will be dealing with two types of matrices. Later, I will give you recent advances also that we have extended that to the case of distance matrices also. But now let me confine myself to the two matrices now, adjacency matrix as well as, even though it is Laplacian, I will call it as G Laplacian because it is not the exact Laplacian matrix. Some changes are there. G came because of that function f, because if you define g of x is equal to x into f of x, then we can have some you can have the details in that paper which I have mentioned earlier on two Laplacian matrices for Q gain graphs. So forget about that G and all. It is some kind of Laplacian matrix. So first we'll deal with adjacency matrix. It's very simple. Just you have Aij as phi Vi Vj if the Vi and Vj are adjacent, and the conjugate if you take the Jith entry as conjugate of the Ijth entry. That's all. Now, yeah, when you have that adjacency matrix, this is Professor Ankur has mentioned. There will be some interesting, what is that, giving and taking policy between linear algebra and graph theory. And this is, you can see the characteristic polynomial, if you want to say that it comes from the linear algebra or the something as associated with a matrix. The right side, the value is computed with the help of the graph parameters. So I think I don't want to go into the details, but let me tell you what are these KL, CL, and etc. You can see that in under the summation symbol there is Li. It is we call it as linear graphs or elementary graphs. So it consists of if Li means if you have AI, then Li consists of all what is it subgraphs of order I, where the components are either a cycle or K2. So the you can see that only cycles come into picture and the K2 edges come into picture inside that expression. So when you have what is that Li, the script letter Li, and if you take it as L, which consists of only cycle and K2 edges, then you can have the ith coefficient of that what is that? Not ith coefficient. It comes along with x to the power of n minus I. We have taken it another way. So this will be the way to compute ith coefficient of the characteristic polynomial. So it's I will say that it's a beautiful interplay between linear algebra and graph theory as such. So this is about the calculation of a computation of coefficients of characteristic polynomial with the help of features from the graph. So let me move ahead. If you want to have the details, it is simple to calculate because it is done with the help of that matrix expansion. So yeah, determinant expansion. Now this is as Professor Ankur has rightly said, when we want to optimize the eigenvalues, this expression will be very useful. In the case of a conjugate skew gain graph, if you have a conjugate skew gain graph as G phi, then for any x belongs to the n tuple from the complex that is space Cn, then it will be x star adjacency matrix of G phi x will be 2 times sigma over the edge. It is not oriented edge. The one edge, the 2 part comes because we have already taken into consideration of the other part VU in the other direction. So it is real part of phi of UV into XU conjugate into XV. This is how that expression will look like. So with the help of this x star A G phi x, that expression you can find bounds, useful bounds for the eigenvalues. So I just mentioned it because if you are interested, we have published only one paper and many things we can do in this area. That's why I just mentioned that idea. Now let me move on to the Laplacian-like or G-Laplacian matrix of conjugate skew gain graphs. So here already have mentioned that we require oriented edges. So take EJ as the oriented edge, VI, VK, where VI is the tail of that edge EJ, and VK is the head of the edge EJ. If that is done, we define, the degree of a vertex. Here we define it as absolute degree dA of V. dA means absolute degree of V as summation of that modulus of phi of E, where E is incident with the vertex V. So that is a suitable G-Laplacian matrix, as I mentioned. It is there in the paper, and we have adopted that same terminology here also. We can, if you want, you can call it as Laplacian also, because we have introduced 2 types of Laplacian matrices, and the second one is G-Laplacian matrix for skew gain graphs, and this is conjugate skew gain graph, a particular case of skew gain graph. Okay, now this is the definition of the G-Laplacian matrix. It is absolute degree diagonal matrix, then consisting of absolute degree of the vertices minus adjacency matrix. In the case of ordinary graph, it will be DG minus AG. Here it is DAG phi, where we have to deal with the sum of the absolute values of the edge gains. Okay. Okay, G-Laplacian matrix, let me emphasize the fact that as we are dealing with one side as Z, in the column it is Z bar, you can see that the matrix we are dealing with will be Hermitian. So that eigenvalues will be all reals, okay? So the G-Laplacian matrix is positive semi-definite. It is another very important feature which we have to consider, because positive definite semi-definite matrix will have what is that, non-negative eigenvalues. So we can prove that LG5 is positively definite. That proof is very simple if we have this expression, just like in the case of adjacency matrix. Here we have X star LG G5 of X will be just that expression. Then you can see that the first quantity, mod phi UV, that's what is real number, which is greater than 0. Mod XU minus mod XV whole square, that's also greater than 0. And you can see that in the second part, plus, after the plus, you can have 2 times modulus of some complex number minus real part of the same complex number. Therefore, it will be again greater than or equal to 0. Therefore, you can see that LG5, G5 is positive semi-definite. Now, you see, in order to connect this G Laplacian with incidence matrix, rather I should call it as oriented incidence matrix. This is how it is defined. If you have a conjugate skew gain graph G5, you can have an incidence matrix F G5, which is, if I call it as entries as Bij. Bij should be done like this. We have to separate the tail and head part of the edge Bij. Then if it is tail, we have to assign Bij as the corresponding to the column of the edge. It must mod phi Ej square, and the we have to take it as minus the of the corresponding edge is mod plus J. Graphs and what is graph, it will be modulus will be 1. Here you see in the case of first row, we have the other two entries as -I and -1. Therefore, the moduli will be, sum will be 1 plus 1. That's why it's 2. In the case of the second row, you can see that first entry is I. Look at I, this is conjugate of -I. And -2I, whose modulus is 2. So 2 plus 1 is 3. That's how it is computed. So matrix tree theorem, that's matrix theorem for sine graphs, matrix tree theorems for gain graphs are there in literature, and this is somewhat we have done in the case of skew gain graph also. That is the reference number 7. So that's extended here. I don't have the time to explain what are there inside that sigma simple. Here we have to have some new definitions, just in the case of just like in the case of computation of coefficients of the characteristic polynomial. Here we should have some kind of see here there is a terminology called essential spanning subgraphs. It means if you want to have in the case of in the case of cycles, as Professor Ankur has rightly mentioned, if it is here we have taken complex values. So determinant of LGG5 will be 0 for those balanced things. And so if it is if there are cycles which are not balanced, then it will be not 0. We have just mentioned that LGG5 is positive semi-definite. So see, it will be having value 0 only when it is balanced. I will come to that point of balance now later. So this figure is drawn just to illustrate what are their quantities inside. I am not moving into that part. Let me move on to some important content. Notion of balance in conjugate skew gain graphs. So let me basically this social mathematical sociology or social social networks analysis and all, we have hatred relationships as well as friendship relationship. That's modeled by sine graphs. In gain graphs, you can have weights from generally from a group and all. But in order to deal with matrices and all, we will take especially rings or higher structures fields and all. We are considering fields of characteristics 0. So here we are extending that concept of balance to the realm of conjugate skew gain graphs from that of the sine graphs, complex unit gain graphs, or generally gain graphs. There and all, I have mentioned that the modulus value will be 1. Here it will be the modulus of that cycle need not be 1. Here you can see that this is how we extended the definition. A conjugate skew gain graph is balanced if the conjugate skew gain of the cycle C, which is computed as I have defined in the one of the previous slides. If every cycles gives you this equation, phi of C is mod phi of C. Mod phi of C, if it is 1, the definition actually coincides with that of the sine graph or gain graph or complex unit gain graph. So this is just an extension extending the things to see. Actually, mod phi C means is a real number which is greater than 0. So if you take it as phi of C as x plus iy, it means x plus iy is equal to root of x square plus y square. Then you can see that y will be 0. Therefore, it's a real part x greater than 0 must be there. That's the thing. Example of a balanced conjugate skew gain graph. There are many cycles. Let me take the outer cycle, that is V1, V2, V3, V4. If you multiply, you can see that will lead to a real number. If you take the triangle V1, V2, V3, but be careful, V1, V2, V3, the edge E1 is from V1 to V2. It is oriented with the gain 1 plus I. Edge E2 from V2 to V3, it is I. That's okay. We are traveling from V1 to back to V1, but when you move along the edge V3, V1, you have to take the thing -1 minus I. If you multiply, it is another real number. So that's see, you can see that everything will be a real number. So it's an example of a balanced CST. So switching, I have already mentioned. In the case of skew gain graphs, we have it as F. Here it is that F becomes conjugation. That's all. So it's a function from vertex set to entire complex plane you can have, but usually this is only required. Units that circle is only is required because we require some. So this is setting that I have taken a very simple case of sine graphs to as the graph on the left side. If you apply on the zeta sigma on the right side, and you see the value Dragicevic and or SACS. That's why it's called SACS formula, which I have mentioned there. This is a basic book we have to read. Then Harari's paper, The Determinant of the Adjacency Matrix of a Graph, must be read the second, third one, you look at the J. Hage and T. Harju, the size of switching classes with skew gains. So these are the two people who worked on skew gain graphs, but they have that motivation from the field of computer science. They wrote the paper for solving some the field of computer science. So other things which you can go through. Another Duff's paper also I'll mention because it is another often frequently cited, spectral properties of complex Euclidean gain graphs. It deals with what is the gain graphs with gains from the unit circle, mod z equal to 1. Okay, so with that I will end my lecture, and I hope the things are conveyed properly, and I must thank once again the organizers for inviting me to this very eminent series of lectures, and I must be thankful to Professor Madhubankal Pei for Madhubankal sir for for having invited me for this function.
Thank you, sir. Thank you. Yes, sir. Continue.
Yes, thank you, Professor Hamid, for your nice presentation. Now the floor is open for question. So one question that I can see in the chat box, that was from Priya Darsani. So she was requesting you to suggest some other example for balanced CSG. She has some confusion with the example that you have provided. Can you hear me?
Which one regarding the balance?
Balanced CSG.
Okay, let me see. Basically, balance theory started with the introduction of sine graphs. It's for the analysis of social networks, where it's used for modeling that hatred or friendship. Means hatredness will be treated as if we have two people, say V1 and V2. If V1 is hating V2, then we'll take the relationship as negative relationship. If V1 loves V2, it will be positive. So if we have a big network of such people, especially in an organization, the question is, having all these rivalries, how balanced that system will be working? How nice the system will be working? Will it be, so to assess that, to ascertain that, Harari and another social psychologist, Norman, suggested this model, and that paper I have just mentioned on the notion of balance in sine graph, that was the first paper written by Harari and all. That is the basic paper, and another one is the paper by Daraski. So after that, gain graph was at the time of introduction, it was called voltage graphs, just to analyze electrical networks and all. Means when something is going from one direction, if it is say some A, going back will be A inverse. So if A inverse, in the case of additive group, it will be minus A. For cash flow management, all we can use that additive group also. So that's how the balance theory came up, and it is now we have extended it to the case of entire complex plane. That's the thing.
I hope you have some idea, a better idea about the concept. So someone is asking for application of this concept.
For the time being, as I just mentioned, we are focusing our attention to analysis of that is social networks with complex weights if we assign. So particular cases are, you can see that complex unit gain graphs and the sign graphs. So these are the areas where several researchers have contributed, and this is only the beginning. I have just shown that paper. That was the beginning in 2023. We have just published it, and we have to explore many things. What are the areas where we can use it?
Right, right. Is there any other question? Okay.
How to construct CSV graph?
Yeah, yeah. So how to construct CSV graph? Another
Yeah,
query.
see, if you have a model and it is dealing with a relationship. So suppose you have, say, n number of people, say V1, V2, etc., Vn, and if we have a relationship, how V1 is related to V2 in one direction. If it is V2 to V1, it will be it should be taken as not the directed graph. Is orientation. If we assign some thing to one direction as some, say, Z, complex number Z, then V2 to V1, it must be Z bar. That's all. That's the basic thing.
Yeah. As the name suggests, it should be congruent, basically. Okay. Any other query?
Most probably there is no question.
Yes. So if there is no question, then let us thank Professor Hamid for his nice deliberation. And it is over to the organizers. Yeah.
Also, our organizing committee, that is SAMS, is grateful as well as thankful to the speaker as well as our chairperson of this session. Thank you, sir. Thank you for your presentation.
Thank you. Welcome.
Next, Srinanda, continue for next session.
Yes, sir. Thank you very much. With this, we have completed our third invited lecture session, and we have come to the fourth invited lecture session of today. So in this session, we have with us the speaker, Dr. Pranjali Sharma, Department of Mathematics from University of Rajasthan, Jaipur. The session will be chaired by Dr. Anita Pal, and I will be the session coordinator. So let me give a very brief introduction about Dr. Pranjali Sharma. Dr. Pranjali is working as an assistant professor in the Department of Mathematics, University of Rajasthan, Jaipur. Earlier, she was teaching at Banasthali University, Niwai Tong. Her area of expertise include problems in algebraic graph theory, labeling problem in sign graphs. She has 10 years of teaching experience. She was a gold medalist in MSc Mathematics and scored the first rank. As an achievement, she was selected for the National Board of Higher Mathematics Fellowship, JRF, to pursue PhD in the area of algebraic graph theory. She has also qualified NET JRF 3 times and GET 2 times. She has published more than 30 research articles in the Journal of International Repute, like Communications in Algebra, Graphs and Combinatorics, and National Academy of Science Letters, Indian Mathematical Society, etc. She is also a reviewer of many international and national journals, including ZB Math. Dr. Pranjali is executive member of Academy of Discrete Mathematics for the period 2024 to 2026. She has delivered more than 21 invited lectures and chaired several sessions at various universities and institutions. She has examined 5 PhD theses and 2 MPhil dissertations. She has developed 4 chapters on graph theory for Institute of Lifelong Learning, Delhi. She has organized many refresher course and faculty development program as a coordinator. I may now request Dr. Anita Pal to please chair the session and introduce as well as welcome the speaker.
Yeah, very good evening. How are you, Dr. Pranjali?
I'm fine, ma'am. What about you?
Yeah, I'm good. So it's good seeing you after many, many years.
Yes, ma'am. We met in 16 physically at NIT Durgapur.
Yes, yes. At that time also you were a speaker of some workshop
Yes,
we have organized in graph theory.
Yes.
So yeah, this I take this opportunity to invite Dr. Pranjali for this session. This is the last session and last lecture of this workshop. And today the title on which Dr. Pranjali is going to talk is Domination in Sine Total Graph of Commutative Rings. So Dr. Pranjali, you can start your presentation.
Okay. Thank you, ma'am.
Thank you.
First of all, I am very thankful to the organizers and of Sridharacharya Academy of Mathematical Sciences. I would just first share the screen so that I can begin with. Am I audible clearly and my screen is visible?
Yes, your screen is visible.
Okay, fine, ma'am. So, first of all, I am very thankful to the organizer, Professor Madhumangal Pal sir and Professor Anita Pal ma'am, giving me opportunity to discuss the research work based on domination in sine total graph. So, since this workshop has been organized in the honor of legend of graph theory, Professor Ambar Sampath Kumar sir, who was a pioneer in graph theory, and he initiated graph theory in India. That's what his birthday is celebrated as a graph theory day in India on 10th June every year. So today I have chosen topic domination because sir was also fond of domination and matrices. Sir has contributed to research in wide domain of graph theory, starting from graph reconstruction, domination, coloring, graph restructures, semigraph, and many more. This photograph was taken during EDMA 2023 and sir has blessed me during new executive members of EDMA 2023. So I'm just remembering and I give my tribute to Professor late E. Sampath Kumar sir. However, he is alive with us, as if we will do good work as he desired, then he will be alive in our memories and in our work. So with this, I will start the lecture. So today, this lecture is based on the concept of domination in the realm of sine graph. The usual domination of graph we are already familiar with. And in fact, it is an area which cannot be forgotten once we counted some topics of graph theory. So here we have initiated this idea into the realm of algebraic sine graph, and sine total graph is one of them. Here we have tried to characterize the commutative ring so that we can see that how the properties of algebraic structure impact on the domination or another parameters. Not only this, during the course of investigation, we have found that the result established in the paper in 2013 was incorrect about the domination number. While we were working for the sine total graph, but when we compared it with total graph, the domination of total graph, then we found that the result, one of them, a result is not correct. And we have also given counter example to substantiate our claim. So how we will go? I will just start with algebraic graph, then sine graph, Later on, we'll discuss what is an algebraic sign graph, and finally, the concept of domination in sign graph. Of course, the lecture ends with some open problems that can be tackled by any one of us. So let us start. What is an algebraic graph? Take an algebraic structure S along with the binary operation star, then graph is called an algebraic graph if the vertex set V is the subset of that set S, which we have taken as an algebraic structure, and the rule of adjacency is coming through the binary operation, because algebraic structure can have more than one binary operation. So any one of them or any one of the binary operation can play a role to define the adjacency rule of algebraic graph. In fact, there are several algebraic graphs in the literature. I am listing few of them. The first one is Cayley graph. We all are familiar with. It was introduced by Arthur Cayley in 1878. And this Cayley graph is based on the algebraic structure group. However, in recent research, Cayley graphs have been constructed on the ring as well. But initially, it was introduced based on the group. Secondly, the zero divisor graph, which was defined by Eastman back in 1988, it is also an algebraic graph by definition, as the vertex set of zero divisor graph is set of zero divisors. However, ring has been taken as an algebraic structure. So zero divisor is subset of R, and here V is using as a ZR. So the first condition is fulfilled. V should be subset of S. And in zero divisor, since ring consists of two binary operations, addition and multiplication, so in zero divisors, we generally use multiplication as a binary operation to define the adjacency rule, because zero divisor is a graph where set of zero divisor is the vertices and the adjacency rule is product of two distinct vertices, because they are labeled with the elements of R, should be 0 under that modulus. If the ring is finite, then modulus will be used. However, I will discuss example in my next slides. The other one are unit graph, total graph, and zero ring graphs. All are the algebraic graphs. These are existing algebraic graphs in the literature. So years also have been mentioned in let us come to the sign graph, because we have to discuss the domination concept in algebraic sign graph. So algebraic graph, we know that algebraic structure should be there. There should be a rule of adjacency using the elements and the binary operation. Now, as Professor Sahul Hamid has already discussed the game graph, and which is a generalization of sign graph. So let us come to sign graph, and I think one of the participants have asked question about balance. So I will come on that concept as well. So on the social psychology front, if we look at the Harari's model, then a network, of course a social network, is represented by a graph where the set of vertices are individual in the social group, and the relationship represents the interactive individual. Means if you have, according to Harari's model in social network analysis, these dots are nothing but the individual, means person 1 and these are person 2. And if they like each other, then this model says that, okay, the positive adjacency is there. And if they dislike each other, then the negative adjacency is there. However, in graph theory, we generally look at the adjacency, but in social network, of course, in the sign graph, we deal with the adjacencies of which kind. Either it is a positive adjacency or it's a negative adjacency. So it is a positive or negative according if this behavior is positive or this attitude is positive towards P2 or it is negative. Now, so this model have been transferred into mathematically. So how we can define mathematically a sign graph? That if you have a graph which consists of vertices as well as edges, in a sign graph, we also have in signature because vertices are there, edges are there, but we require a function from the set of edges to plus and minus. Means here now edges are either labeled by +1 or -1. The edge which receive the positive sign will be known as the positive edge, and the edge which receive the negative sign will be known as the negative edge. Now, how we can say the sign graph is a generalization of graph? Because if a sign graph consists of all positive edges, then it is called all positive, and it is the graph which generally we talk about. A sign graph is said to be homogeneous if it is either an all positive or all negative, and heterogeneous otherwise. Now, let us have some example of sign graph. So, suppose you have a vertex, two vertices. Participants, please be careful if I'm not audible and my slide is not visual. Please let me know, otherwise I would not be knowing. Suppose this is a graph. Now, how many sign graphs we can construct on this particular graph? This pen is not properly working. Let me choose another color. Suppose this is a graph. Forget about this. Is a these three vertices. G consists of three vertices, and now I'm just constructing a sign graph. Here, all these two edges are negative. It might be possible that one edge is positive and one edge is negative. Yes. This is also possible. This edge is negative. Yes. This is also possible that all the edges are positive. So given a graph, we can construct many sign graph on that graph. So this is just a basic example like we start with. So how many function you can define, because if there are two edges, then of course both can be plus plus, one can be plus minus, and minus plus and minus minus. So these are the sign graph on this particular graph. It is nothing but the path on three vertices. Now, the concept, I think one of the participants were asking how to see, but I will discuss here balance in sign graph, and that is the generalization which Professor Hamid was talking about. So first of all, here there can be cycle in a graph, or it can be it does not have a cycle. But the concept of balanced in a sign graph, because this concept has been induced from social network analysis. So we want that system should be balanced. System should be balanced means there should not be any stress. Suppose we have many people in an office working together and they don't like each other, then system will not be balanced in that case. So if we want systems should be balanced, then we will look at these cycles. A cycle in a sine graph, we will denote this by sigma, means we will denote sigma, which is VE, and the signature. Means the original graph now consists of signature as well. So a cycle is said to be positive if the product of the sign of the edges is positive and negative otherwise. Means, suppose this is a sine graph consisting of only one negative edge. I'm taking example, so I'm starting from scratch only, then I will go on higher. So here, this is a cycle in sine graph, this is also a cycle in sine graph, and automatically this is also a cycle in sine graph. Now we will look at this. This is positive edge, this is also positive edge, this is negative, this is positive, this is positive. So now if we just product of the sign, what is the sign? Of course, plus, plus and minus, so it is minus. So sign of V2, V1, V2, V3 is nothing but the negative. So this cycle is a negative cycle. Similarly, this cycle is also negative. But if we look at the V1, V2, V3, V4, this cycle is a positive cycle. So sine graph is said to be balanced if every cycle in sigma is positive. Means we have to look each and every cycle. Every cycle in sigma is positive, then only the sine graph is balanced, otherwise not. So if we look at this sine graph, this is not balanced because there exists a cycle which is negative here. And negative cycle would create a stress in the system. So that will not be, the system will not remain balanced in that case. So let us again look at the concept of balanced and unbalanced. Suppose there are three people, A, B, C. In the first case, all are friends. Positivity means if A like B. A like me means they have the same thoughts and on. So this is positive, this is positive, this is positive. Means A, B, C like mutual friends or like each other. Here, if we look at the situation, this situation can be understood by an example. Suppose A is a girl and there are two boys, B and C. B and C like A, both like A. Then in that case, B and C cannot be good friends. There will be stress in between B and C. So this is not balanced. This sine graph, if such a structure will be present in a sine graph, then definitely that would not be balanced because product of the sign of plus, plus and minus will be minus, negative. So this is nothing but a negative cycle. If we look at here, then here C is a common enemy of A and B. A don't like C, B also does not like C. So A and B can go together, but they don't like C. So there will not be any stress because C will be out or C will be isolated from that. But in this case, plus, negative, negative, multiply all these, that will be plus. So system will remain balanced, or I would say that this structure is balanced. Here also, all three are working together, living together, because they are adjacencies between A, B, C, but they don't like each other. So system will not be balanced. It is also unbalanced. So this is unbalanced, this is unbalanced, these both are balanced. I hope this is clear for everyone. Now I just come back to my objective. Of course, by taking algebraic structure, and here particularly I am taking commutative ring with unity and domination on the graph as well as associated sign graph. So how we will go? Yes, sign total graph. So I will just take few minutes to define total graph, because total graph was not covered earlier here. So total graph is a graph. Let R be commutative ring with unity, and unity should not be equal to 0. Let ZR be its set of zero divisors. Then total graph of commutative ring with unity is a graph where V is nothing but all the elements of R, and two vertices A and B belonging to R are adjacent if and only if A plus B is a member of R. So you are taking each element of R as its vertices, and the